Welcome back to Knowledge is Power Educational Videos, the only place where you can get smarter by listening to dumb people. This is the engineering problem solving section. We are on lecture 3. Today we're going to be discussing density and specific gravity, as well as Newton's second law of motion, force, and weight. So let's jump into density here. So density is simple in concept. It's a measure, and we notate density with the Greek letter rho, which is going to be a sort of swoopy p, swoopy lowercase p. Density is going to be equal to a mass over a volume. I don't like this brush size so much. Let me bring it back a little bit. Mass over a volume. Test it out. There we go. So, simply put, you're just looking at how much of a substance we have crammed into what volume? Into this volume. In a volume. A lot of people like to think about the old joke or trick question they would use, where they'd say, which weighs more, a pound of feathers or a pound of bricks? I mean, they're going to weigh the same, but the feathers are going to take up a lot more space, and they're not as condensed and tight as those bricks are. So, I mean, you might have a whole bag of feathers and just like one or two bricks to meet that pound requirement, right? So it's important to consider that and think about when we're looking at density, the density of the bricks is going to be much larger because we're going to have more mass in a smaller volume. Whereas when we flip it around for the feathers, we're going to have less mass in a larger volume. You see what I mean? So that's one thing to consider. Something else you're going to see when you're out there working, we're not going to use it, but we're going to discuss it and make sure that you're aware of it, is you might see the Greek letter gamma, the lowercase gamma, which is just a really cool looking Y. I feel like that's not going to be seen. Let me turn the brush size up just a little bit more here. Sorry, guys. All right, let's try this. There we go. Y. That's ugly. Let's do it again. Y. And this is equal to what we call specific weight. Specific weight, which is equal to, this is basically the weight of an object divided by the volume. Now, that's something that we're gonna just put it out there and make sure you know W over V for short. Make sure you know it, but it's not necessarily something we're gonna use. We're mostly gonna focus on something called specific gravity. And what this is this is the density of an object over the density of water. Now, key thing to remember about specific gravity, and we're just going to do this very short and very sweet. We're not going to go into a whole bunch of information on this. But the key thing to remember about specific gravity is it's going to be unitless. And let me explain. Up here we have a mass divided by a volume to reach density, right? That's what we got going on there. So let's imagine the density of our object is 1,000. Let's bring it back. 1,500 kilograms per meters cubed. And let's imagine that our density of water is 1,000, and this is an actual density of water, kilograms per cubic meters. What happens? When we divide these two, we end up with a value, and these units cancel. So something to remember is SG, our specific gravity, is unitless. Okay? And that's pretty much the gist of the whole deal here. Let's go over some of the common density of waters, and this is something you actually need to either retain and remember to work out the problems that are assigned, or you need to probably make a cheat sheet and have it on hand and ready to go. Normally on a test or something like that, they'll go ahead and give you the required density of water for the problem, but if you're working on the homework assignments and stuff, you'll have to reference this. So common density of water is going to be 1 gram per cubic centimeter. There's 1 kilogram per liter. There's 1,000, this is the most common in my opinion, kilograms per meter cubed. Let's see. The other ones you probably won't use, but we'll put them up here though. 62.4 pound mass per cubic foot and 1.94 slug per cubic foot. So those are the more common densities of water, and all of this can be for the most part manipulated algebraically. So if you have a specific gravity and you have a density of water, you can then multiply both sides by the density of water, and what you're left with is you have the density of your object is equal to the specific gravity times the density of water. And the same goes with density itself. And we're going to do an example at the end of this lecture. So we'll just move on now onto the next section here, and we're going to talk about. Let's bring it down. And now we're going to talk about force and weight. And if you guys remember early on, I started planting the seed. I said don't consider mass to be weight. And so we're going to kind of prove and disprove that at the same time here, because there's a certain property and a certain unit that we use that it can be argued. But we're going to go ahead. Let's jump right into it. So force, as defined by Newton's second law of motion, is simply defined as the acceleration. We're just going to do A for that. Required to move a body of mass. So force is equal to mass times acceleration. Now, the concept here is simple. If you imagine just pushing a shopping cart, you have a body of mass inside this shopping cart, and as you push it, you're going to continue to get a little bit quicker and a little bit quicker. You're going to accelerate, so what you're exerting over this shopping cart by pushing it is force. And that's how force works. Now, force in SI, or standard unit, the standard system, the metric system, the mass for force will be kilogram. The acceleration will be meters per second squared. And force, 1 Newton, which is our unit for force, is equal to 1 kilogram meter per second squared. Now that's the SI. Now in the AES, American Engineering System, people get confused because mass, they want to say mass is pounds mass. And it's not. It's slug. Your acceleration is in feet per second squared. And your force is 1 pound force, which is equal to 32.2 feet per, bring it back here, slug feet per second squared. Quick correction, guys. My apologies. I put down that 1 pound force is equal to 32.2 slug foot per second squared. That is incorrect. So I just want you to imagine right here that I had said it is equal to 1 slug foot per second squared. My apologies. Now, why slug? Why are we doing slug? What is slug and why? In solving these problems later on, the more you do them, you're going to learn that it gets very confusing for people when they're dealing with pounds mass and pound force. Because in Earth's gravity, which is 9.81 meters per second squared, or if we convert that, 32.2 feet per second squared. And let's do the conversion real quick just to be sure. Meters second squared. 1 meter is 3.28 feet. And this comes out to, let's break out our calculator. I'm going to do 9.81. Move it over so you can see what we got going on. Times 3.28, 32.17, or, whoops, tool got switched, 32.2, oh, yeah, feet per second squared. So, people get confused here because, let's take for instance, we have exactly 1 pound mass. We multiply this times 32.2 feet per second squared, which is the acceleration due to gravity on Earth, and we get 32.2 pound mass feet per second squared, which pound mass feet per second squared, let's convert that, pound mass feet per second squared, and we're going to put 32.2, and what we're going to do is we're going to convert pound mass to slugs. So that's going to be 1 slug is equal to 32.2 pound mass, and we come out to 1 slug foot per second squared. You see? Which is equal to 1 pound force. So we have found that 1 pound mass is equal to 1 pound force in Earth's gravity. The problem comes when students attempt to do a question that uses, let's say for instance, we're talking about Mars gravity. Mars gravity, sloppy, G Mars is equal to 3.7 meters per second squared. So we're going to convert this. We're going to just scribble over that. We'll put second squared down here. 3.7 meters per second squared. We know 1 meter is 3.28 feet. And we come out to, let's break out our calculator again. Oh, we got 2 calculators up for some reason. Let's break out our calculator again. We're going to do 3.7 times, it should be like 12 point something. 3.28, 12.13. 12.13, actually it was 136, so we're going to do 12.14 feet per second squared. And this is going to be equal to the Mars gravity. So now, let's say as an example, we're trying to figure out the force of an object on Mars gravity, and we want the final force in pounds force. And let's say this thing weighs 5 pounds mass. What students will try to do is they'll try to say 5 pound mass times Mars gravity, 12.14 foot per second squared, equals, and what is that? Let's see, times 5, 60.68. 60.68 pounds force. This is incorrect. This is entirely incorrect. We don't have pounds force here. That's not our units. What our units are is pound mass foot per seconds squared. Okay? Now if we convert our pounds mass to force, we find one slug is equal to 32.2 pound mass. And then we get, let's bring this bad boy back up. Let's move it over so we can see. 60.68 divided by 32.2, 1.88. 1.88. And this is finally in pounds force, because our units here would be slug foot per seconds squared. So it's important that you understand this, because you don't want to get your answers wrong, especially on the test. This does not equate to a pounds force. So to further define it, let's talk about this. 1 pound force is equal to 1 slug foot per seconds squared. Also, 1 pound force can be used, and it is equal to 32.2 pound mass foot per second squared. Okay? So just don't get confused thinking that because you multiply. Now this process right here to here would entirely work if we were using Earth's gravity. If our gravity was 32.2 foot per second squared. Only in Earth, and let's prove it one time, because we proved it up here with 1. Let's prove it with 5. So 5 pound mass, okay, times 32.2 foot per second squared is equal to, and let's multiply that bad boy out. 5 times 32.2, 161. 161 pound mass foot second squared. Now let's convert. 1 slug is 32.2 pound mass. And so that number here divided by 32.2 is 5. 5 slug foot per second squared, or 5 pound force. It's as simple as that, guys. 1 pound mass is equal to 1 pound force, but only when we're dealing with Earth's gravity. Now let's talk about weight. Everybody wants to confuse weight with mass. But weight is not a mass. If you imagine what you're doing when you step on a scale to weigh yourself, you're stepping on a scale and it's measuring what gravity is doing to the mass of your body. Weight is a force. So force is equal to mass times acceleration. Weight is equal to your mass times gravity, which is what we proved in the previous lecture, was that gravity is a form of acceleration. So that should be a simple concept to you at this point. We've explained everything else up to here, so this should be a very, very simple concept to you, and we've proven how we come to the conclusion of the 9.81 meters per second squared and everything. So the concept of weight being a force should be something that you can put together very easily, and it should make perfect sense to you, I would hope, at this point. Now, let's do an example problem. Let me think here. We want to solve a example problem. Let's do what? And we're going to give ourselves some room here. Example problem. me just check over here, make sure that that's showing up this time, because I know on my previous lectures I'd written off the screen a little bit, so I've tried to correct that. What is the weight? Oops. Of water in pounds force. Let's see. What is the weight of water in pounds force in a 55-gallon drum that is full? So we're using the full 55 gallons. And the density of water, we'll say raw water, is equal to 1 gram per cubic centimeter. And we're going to ignore the weight of the drum. So what we want to know is, we have a 55-gallon drum. It's filled to the top with water. We want to know the weight of that water, and we don't want to know the weight of the drum. We just want to know the weight of that water. So the first thing we're going to know is we know that weight is equal to mass times gravity. Now, we don't specify where this is in the universe, so we're assuming it's going to be on Earth, which means that it's going to be 9.81. So we're going to put that up here. Gravity is equal to 9.81 meters per second squared, or 32.2 feet per second squared. Since we're going to be using pounds force as our final unit, we want to make sure that we also put the 32.2 up. Now we have, in this equation, all we have right now, we have weight is equal to mass times gravity. We don't have a mass. We have a gravity, we don't have weight, we don't have a mass. So we need to find mass. Now, what we do have is we have that it's water and we have the density of water. So let's put a new equation up. Density is equal to mass over volume. Right? Or just M over V. I mean, that's how we're not going to write it out every time, but in the future it'll be just M over V. So we know density, and we have a density of water, so our density is equal to, well, that was sloppy. Let's try that again. Our density is equal to 1 gram per cubic centimeter. And our volume, we have a volume too. We have 55 gallons. So our volume is equal to 55 gallons. Okay, so that's not so bad. So let's start playing with this. Let's start doing some conversions. First off, we know we have in density, anytime we have an equation like this, as long as we can get everything but one, we can solve for the one that we're missing. So we know we have a density, we know we have a volume, we don't have a mass. And we're going to solve for mass. But first we got to get these units here to where they'll actually cancel and they're usable. So in order to do that, what we're going to do is we're going to first take 55 gallons. And we're going to convert it. 1 liter is 0.264 gallons. Okay. And we're going to do 1,000 liters is 1 meter cubed. And this is going to bring us to, let's break out our calculator. Let's clear. 55 divided by 0.264 brings us to that, and then we're going to divide that by 1,000, and we get 0.208 cubic meters. Because our units cancel, so let's make sure we clear that out. Gallons are going to cancel here, liters are going to cancel here, leaving us only with this, and I said it was 0.208 meters cubed. All right, now we have a new volume unit. Now let's take our density and let's get it to meters cubed too. So we're going to say 1 gram per centimeter cubed. Let's bring this on out. Is 1 kilogram is 1,000 grams. Okay. And what do we got? Cubic centimeters. So that's going to be, we know that, and you guys got to go back to the rules of exponents we went over earlier. We know that 1 centimeter, or I'm sorry, 1 meter contains 100 centimeters. So, but we're dealing with cubic, and we have to carry. If we're looking at the cubic, we have to carry. Remember, if it's this what was it? AB raised to the 3 is equal to A to the 3, B to the 3, right? We had to carry this into both of these. So that means that if we're doing, if 1 meter is equal to 100 centimeters, then for centimeters cubed, it would need to be 100 cubed to reach 1 cubic meter. Okay? So with that written out, let's find out what that's equal to. Let's break out our calculator. Bring it up over here. So we're going to take 1 divided by 1,000. And then we're going to multiply this times 100. And we're going to cube that. 1,000. And our units cancel. So here we cancel grams, leaving ourselves with kilograms. Here we cancel cubic centimeters, leaving ourselves with meters cubed. And we come out to 1,000 kilograms per meter cubed. And if we scroll up real quick, and we'll do it just for fun, and we look at the density of water that we discussed earlier, you notice that we have it right here. Let me change the color so it's a little more noticeable. We have it right here, 1,000 kilograms per cubic meter. So we know that to be correct. Now let's go back down. Now, we have density is equal to mass over volume. And right now we have a volume and we have a density. We need a mass, which means that we need to get mass by itself. So we're going to multiply both sides of the equation by volume, and that's going to bring us to mass is equal to density times volume. So let's set that up. Mass is equal to our density, which is 1,000. Here, let me take that parenthesis off. We're going to do this just like a conversion, really. 1,000 kilogram per meter cubed. And that's going to be times our volume, which is 0.203 meter cubed. And look what happens here. Look what happens here. Our meters cubed cancels. So this is going to multiply out to, and just to be safe, I know this is one that everybody goes, oh, you could do this in your head, Randy, but let's just be safe. 0.203 is 203. 203. And all we're left with is kilograms is equal to mass. So we found a mass now. That was simple enough, right? Oh, you know what? 208. Uh-oh. I just realized right here, guys, if you can see where I'm drawing those arrows, this was supposed to be an 8. So that means this is supposed to be an 8. My apologies. So 208 kilograms is equal to mass. Now, let's look at our equation. Weight equals mass times gravity. Now we have a value for both mass and gravity. So let's set it up. Weight is equal to 208, and we got it in kilograms. So in order to be able to cancel these, we're going to go ahead and use our 9.81 meters per second squared. We're going to use our meters per second squared version, and we'll just convert later. So what does this bring us to? 208 times, let's correct this, times 9.81. It's going to bring us to, oh, that doesn't look good. The work, I have it already pre-worked out, so just to be safe, maybe I just did it by 9.8, or yeah, there it is. Okay, so that's where I made the mistake. So that's going to bring us to 2038 kilogram meters per seconds squared. And what do we know about that? We know that, matter of fact, let me bring this back, per second squared. And we know that, we're going to do it right here, this conversion, 1 kilogram meter per second squared is 1 Newton. So that's going to give us 2038 newtons. And now we have our weight, but it's in the form of newtons, and our question called for pounds force. So there's simply one more conversion that needs to take place. We need to take 2038 newtons, and we need to convert this over to pounds force. And that's a direct conversion because it's force for force. So 1 newton is equal to 0.225 pounds force, which brings us out to, let's do the math. Let's do 2038 times 0.225, and there we go. 458. 458 point, what was it? 55.55 pounds force. Or you could say weight is about 460 pounds force. So just for fun and to check our work, let's go ahead and Google how much does a gallon of water weigh in pounds. I have it pulled up right here. We'll bring it over to the screen for us. And it says a gallon of water weighs 8.34 pounds. 8.34 pounds. So let's take 8.34, and in this equation, we did 55 gallons. We're going to multiply by 55. And look what we get. 458.7. We were very, very close to the accurate answer there. But then again, you know, a gallon of water doesn't weigh exactly 8.34. There's going to be some additional decimals, and if we add those in and then we didn't use any of the rounding in our equation, we would have come to the exact same solution, guys. All right, thank you for tuning in. You have a wonderful day. We'll see you guys at Lecture 4.